So last time we defined the basic uh, concepts of sampling theory. So we have what is called a population, that is just a distribution about which we don't have complete information. So for example, if the population is suppose a normal distribution, then in order to get the complete information about the distribution, we need to know its mean and variance, because the normal distribution is completely defined by its mean mu and variance sigma square. So suppose you don't have the complete information about this. For example, mu is unknown, or sigma square is unknown, or both are unknown. These are different possibilities. In that case, in order to get some information about this distribution or population, we collect what is called a sample. So a sample is obtained by repeatedly observing the population in a random and independent manner. So random meaning that in practice, you do not select the sample items by using some criterion. You do it as randomly as possible. So there are methods to make sure that it is random and that you don't introduce any unintentional bias into the process of sampling. So using these techniques, you get what is called as random sample, and independent meaning that the items that have already been observed should not influence the uh, items that will be observed later. Or in other words, again, this is also a matter of bias. You should not collect the sample according to some criterion which makes them interdependent. So you have what is called a random sample or independent random sample, which is just an independent, identically distributed collection of random variables. So independent, identically distributed means each of these x1, x2, xn, each xi is drawn from the same population, same distribution. So each one you can say is a copy of a particular random variable x with a particular distribution, and they are all independent. So independent in the technical sense, where if you find the joint PDF of this as an n-dimensional random variable, it is exactly the product of the individual PDFs, all of which are basically the PDF of x itself. Only that you have x1, x2, etc. So you get n different variables. So that is independent sample, and the number of items in the sample is called the sample size. Now the population parameters are, as I said, the mean, variance, or other constants associated with the population. So constant as in it may be unknown, but it is some parameter of the population rather than a random variable. So for example, in the binomial distribution, if you take BNP, this n being different, not this, I don't mean the sample size, your basic population itself is BNP. Then n and p are parameters of the population of this binomial distribution. So one or both of them may be unknown. Now a statistic, on the other hand, is something like a parameter, but the difference is the statistic is defined on the sample. So it is a function of the sample and determined by the sample itself. And of course, whatever population parameters are there also may be involved when you compute the statistic. But in the definition of the statistic, these population parameters are not involved. So that means when you compute the value of the statistic for a given sample, the sample itself is determined by the population, which is determined in turn by its parameters. So indirectly, the statistic's value will be determined to some extent or to the complete extent by the parameters of the population. But the definition of the statistic is independent of any unknown parameters of the population. If there is a known parameter, you can use it, but any unknown parameter is not used. So in the example, it will be clear. So we defined two particular statistics, namely the sample mean and sample variance. So suppose x1, etc., xn is the random sample that we defined just now. And suppose the distribution from which you're drawing this sample, that is the population, has mean mu and variance sigma square. So let me be clear, this is the population mean and population variance. We are just about to define sample mean and variance. So the sample mean of this sample is denoted x bar and is defined as the average of these random variables, these n random variables, the simple arithmetic mean. That is 1 by n, x1 plus x2 plus etc. xn. So you can see that this definition does not depend on the population parameters at all. Whereas, as we'll see here, the value may depend on that, but the definition is independent of that. So when you define it, it should be only in terms of x1 etc. xn. And if you have any known parameters, that could be included. But in the sample mean, this is the definition. Similarly, the sample variance S square, capital S square, is defined as 1 by n summation xi minus x bar the whole square, or it's also, you can also define it as 1 by n summation xi square minus x bar square. So to be clear, this bracket is over here. Okay. So these two are equal. You can easily prove that these two are equal, just like we prove the shortcut formula for the variance in the probability distribution. In the same way, these two are equal. So either of these can be taken as definition. And again, let me remind you, in one of the two reference books, that is P.L. Mayer, the definition is 1 by n minus 1 of this summation. That's a different definition of sample variance. Both are definitions that are commonly used for different reasons. Each definition has an advantage and a disadvantage. So we are going to use this definition, which is found in the textbook Introduction to Mathematical Statistics by Hogg and Craig. So that is your reference book for this chapter. Oh. Okay. So now, last time we proved this. The sample mean itself is obviously a random variable because x1 etc. xn are all random variables, and you're just computing a function of them. So this is also a random variable. We have already seen functions of random variables where you determine distributions of some one-dimensional or two-dimensional, some function of one-dimensional or two-dimensional random variable. So here, this is also a function of an n-dimensional random variable, and therefore it is itself a random variable. And its mean is mu. That is the same as the population mean. So notice that the sample mean is something different from the population mean. First of all, the population mean is a constant. Whether it's known or unknown, it's a constant. It is a parameter of the population. It's a number. Whereas the sample mean, by definition, is a random variable. When you make an observation by taking a particular sample, you may get a value here, but the sample mean itself is a random variable. So what we are saying here is the mean of this random variable happens to be equal to the population mean. Again, whether that is unknown or known, this will be the mean of the sample mean. Similarly, its variance will be sigma square by n, where sigma square is a population variance and n is the sample size. So here the difference is clear. We are taking the variance of the sample mean, and its variance is determined by both the population variance and the sample size. So if you increase the sample size, this will clearly decrease. And we saw the intuition behind this also. When you take larger and larger samples, the sample means variance will obviously go down. This is something you know from experience as well. Notice that the sample variance is very different from the variance of the sample mean. The sample mean is this particular random variable. Its variance is a number, that is the sample variance. That is the variance of the sample mean. Whereas the sample variance is a random variable, just like this. And these are not related, they are not the same thing. Another result that we use for the problems today is if the population here, so that the distribution of these xi's is normal with mean mu and variance sigma square, as already stated. So if the distribution is normal, then X bar itself has normal distribution with this mean and this variance. So that is n mu sigma square by n. This is from an already known property. Recall the reproductive property of the normal distribution. So this is from the reproductive property of normal distribution. That is, if you have x following n mu1 sigma 1 square and y following n of mu2 sigma 2 square, and if these are independent, then ax plus by follows n of a mu1 plus b mu2 comma a square sigma 1 square plus b square sigma 2 square. This is called the reproductive property. So clearly, if you take n different random variables x1 etc xn, all of which have the same distribution n mu sigma square, and if they are all independent, so that's what we have in the sample. These are n independent identically distributed random variables, and in this case we are assuming they're all from the same normal distribution, so that's important. Here we have not assumed that. In this particular case we are assuming that. In that case, according to the obvious generalization of this, which can be obtained by repeatedly applying this theorem itself, we get x bar follows n mu sigma square by n. So firstly, if you look at summation xi, that will follow. You have n different xi's, all with mean mu. So that will add up to n mu according to this, because we are adding n of them. And here you have sigma square also, and those will also add up. So it's not n square sigma square, because we are just adding them. So we get n sigma square. And so if you divide this by n, again just applying this to one random variable. So if you can notice that if it's just ax without the by, or if you take b to be 0, for example, if it's just ax, here you'll get a mu1. So here that a is 1 by n. So 1 by n of n mu, that is mu. And here you will get, now you are multiplying by a constant, not adding n different things, multiplying by 1 by n. So this will be a square. Here a is 1 by n. So 1 by n square of n sigma square, that is sigma square by n. So that's one way to prove this using the reproductive property. Or if you know the property, then we have already found that in any case, whatever be the distribution, in any case, E of x bar is mu and V of x bar is sigma square by n. And from the reproductive property, we know that it is some normal distribution. But if we know independently that it's normal and this is the mean and this is the variance, we just combine those two and immediately get this. So two different ways to prove this. So please make a note of this theorem. This is what we'll be using for the problems now. So the first problem, it is given that x bar is the sample mean of a sample of size 25 drawn from a population that is normally distributed with mean 75 and variance 100. So remember that this is mean and this is sigma square, not sigma. So we are asked to compute the probability of x bar lying between 71 and 79. Recall again, sample mean is a random variable. That is why we can find this probability. Okay, so firstly, we are given the sample size is n equals 25. Okay. Then the population follows n 7500, so that the population mean is 75 and the population variance is 100. Okay, that is 10 square. Okay, then we know from the theorem just stated that x bar will follow n mu sigma square by n, that is n 75, that is the same, and 100 square by 25, that is 4, which I'll write as 2 square because I want to emphasize that it is sigma square, so that sigma is 2, not sigma. This will be sigma by root n rather, right? So this mean is 75 and this variance is 2 square. The standard deviation is 2. Now it's just a normal distribution problem. We just have to compute probability of 71 less than x bar less than 79, and as usual you convert it to the standard normal form and use the normal distribution tables for this. So here what are we subtracting? The mean is 75 and the standard deviation is 2. Okay, so I'll write it as standard deviation is 2 less than z, x bar minus its mean by its standard deviation, that will be standard normal z. Similarly 79 minus 75 by 2. So this is in fact pi of minus 2 minus, sorry, the first one, this one, pi of 2 minus phi of minus 2, which is 2 times phi of 2 minus 1. And if you have your normal distribution table, just look up the probability. So you just have to compute this. Okay, that will be, I think, that's probably it, unless I've made some mistake in the computation. Okay, anyway, this is the answer. You just have to compute the final step. So to review, we are given that the sample size is 25 and the population is normal with mean mu, mean 75 and variance sigma, variance 100. And we are asked to compute a probability involving the sample mean. But from the theorem we saw just now, we know that the sample mean also has a normal distribution with mean mu equal to 75 and variance sigma square by n, which is 100 by 25 equal to 4. Then it just becomes a usual normal distribution problem. The next one, very similar. Again, you are given the sample size, 5 in this case, and population mean is 0, population variance is 125, and the population is normal. So X does follow a normal distribution. Therefore, we know that X bar will follow. So we have to compute something with X bar. So we know that X bar will follow N 0, 125 by 5. That is N 0, 25, which I'll write as 5 square. So the standard deviation is 5 for the sample mean. Okay, now we are asked to find not the probability, but the value C, so that this probability is equal to 0.9. But then this is just phi. So phi of C is equal to 0.9. So again, from the table, just do the reverse lookup. So find the value, find the probability that is closest to 0.9. And that is around 1.28. That occurs at the point 1.28. So this is the Z value. So that probability of Z less than or equal to Z is approximately 0.9. Okay, it will be actually 0.8997. That is the closest that you can get to 0.9 in the table. All right. So these two similar problems. Now here, two samples are given to us. First is x1 to x25, which is a sample of size 25, and another y1 to y25, which is also a sample of 25. Both are independent random samples, but the first one is from N016, and the other one is from N119. And we are asked to compute again something with the sample means, but this time there are two sample means involved. So x bar and y bar. We are not computing separate probabilities also for something with x bar and something with y bar. It is probability of x bar greater than y bar. So how do you compute the probability comparing two sample means? In general, it might be a difficult problem, but again here, these are independent normal distributions. So luckily here, we know that x bar will follow the normal distribution 0, 16 by 25. So I'll not write elaborately the separate population mean and variance. We know that 16 is there and the sample size is 25. So 16 by 25. And similarly, y bar follows n1, that is this population mean 1 of y, and 19 by 25. Okay. So we have these two, but how do you compare them? So usually if you are given such a problem, it is a question of two-dimensional random variable. So now forget the samples and sampling. We just have two independent random variables whose distributions are known. We just have to compute this probability. So usually we would set this up as a two-dimensional random variable problem and then compute the area under the curve and so on. But firstly, these are two normal distributions. So you probably cannot find the answer by integrating anything because the integral would involve in non-integrable functions, e to the power minus x square or something more complicated. But again, luckily, these are normal distributions and we can rewrite the question in this way. Probability of x bar greater than y bar is probability of x bar minus y bar greater than 0. What is the advantage of rewriting it this way? We can again use the reproductive property of normal distributions. So these are independent. There's nothing given about the samples being dependent. Both are in fact independent random samples themselves. They are independent. So these are independent and normally distributed with these particular normal distributions. So what we know is that x bar minus y bar, which is in the form ax plus by, right, also has a normal distribution with mean a mu plus a mu1 plus b mu2, mu1 being this and mu2 being this, a being 1 and b being minus 1. So here you will have I'll write it explicitly. 1 times the mean of x bar minus 1. So minus 1 is the b times the mean of y bar, that is 1. And the sample variance will be what? Will it be 16 by 25 minus 19 by 25? As soon as you think about that, if you did, you should immediately know that that's wrong, because you're getting negative 3 by 25, and negative values cannot be the variance. So the variances never get subtracted, they only get added, like errors. You cannot subtract errors, you cannot subtract variances when you subtract random variables also. So what is happening is, again you have a x bar minus plus b y bar, where a is 1 and b is minus 1. But remember that you have, in the case of variance, you will get a square sigma 1 square plus b square sigma 2 square. So what we'll have here is, again if I write it explicitly, it's 1 square times the variance of x bar plus minus 1 square times the variance of y bar. So that minus 1 square also becomes positive. So this is n of minus 1, which is not a problem, mean can be negative, times 16 plus 19, so 35 by 25, that's 7 by 5. The last part, okay, I'll explain this again. So recall, we have the reproductive property says that if x follows n mu 1 sigma 1 square and y follows n mu 2 sigma 2 square, then ax plus by, where a and b are constants, follows n a mu 1 plus b mu 2 comma a1 square sigma 1 square plus, well, not a1 square, a square plus b square sigma 2 square, okay, plus b square sigma 2 square. So in this case, we have x bar instead of x and y bar instead of y. This is mu 1, this is sigma 1. Well, this is sigma 1 square, right? And this is mu 2, and this is sigma 2 square. And this can be written as 1 x bar plus minus 1 y bar. So a is 1 and b is minus 1. So here we have a mu 1 plus b mu 2, which is 1 times 0 minus 1 times 1, and a square sigma 1 square plus b square sigma 2 square. That's only from this, and because both of these have normal distributions. So computing all this, we get n of minus 1 comma 35 by 25, which is 7 by 5. So again, recall what we want is the computation. We will be using standard deviation, which is square root of 7 by 5. Okay. And so what we want now is, if you call this z, well, not, I don't want to call it z. If you call this random variable, say w, this is probability of w greater than 0. And what is the distribution of w? It's this. So now again, this is a simple normal distribution problem. We only have to compute the probability that, one second. Yeah, we only have to compute the probability that W is greater than 0, where W follows a normal distribution with mean minus 1, and variance 7 by 5. So as usual, this is probability of Z greater than 0 minus 1. So basically minus mu by sigma divided by root of 7 by 5, which is probability of Z greater than root of 5 by 7, which is 1 minus phi of root 5 by 7, taking the complement. So you just compute this. Okay. 1 minus phi of, so that is 0.7995. That's 0.2. Okay. So this is not anything really new. We have already been doing problems on, we did 2 problems on sample means. So that's the same thing. The only difference here is you have to use the property of normal distribution to rewrite this and get and rephrase it in terms of a new normal random variable. That's the only thing. So this question, such a question cannot be asked with most other distributions, because then you would have to compute probability of a 2-dimensional random variable by integration and so on. And so that if it is already the sample mean of some other distribution, it will probably have a complicated distribution. So this will be something which is very difficult to compute. So this is possible as far as textbook problems or exams are concerned. It's possible only with normal distributions. So next time we will see, even if we don't know the distribution of the population. So in this case, we know that it's normal. Suppose we don't have a normal distribution. Even in that case, if the sample size is large enough, then we can still do the same thing. Then the sample mean will still follow the normal distribution approximately. So just like the Poisson distribution is the limiting case of the binomial distribution, and the normal distribution in general is a limiting case of any distribution if you take a large enough sample. That is called the central limit theorem. We'll discuss that the next time.